I'm sorry. That's okay.
Good afternoon. Just a little bit of background. Berlin Energy has 3 different types of reactors running. One of them, 2 of them are with the hot tubes. They're just hydrogen or deuterium gas on nickel solids. And I'm going to talk about, I'm going to talk about the most recent experiment that's been running up in the Berlin and Berkeley lab, and directly after me, Mike Hellam's going to talk about the older type of experiment. So these are totally different calibers. Oh, good. This is my outline. I'm not going to spend too much time on the controlled electron capture. If any of you want to discuss that, you'll have to get a hold of Robert Goddess. That's not part of my presentation. And yes, that is his controlled electron capture. Bottom line, he feels by stimulating the lattice electrically, he can have an electron get excited to have enough energy to be captured by a proton, form a neutron. It's a very exciting neutron. Starts by reacting with a proton, and you climb up the ladder to deuterium, and you do it again, it goes up to tritium, and then if it does it again, it goes up to quadrium, and you get that amount of energy, 20 MeV on the top, by only putting in a couple of MeV. Okay. All right. In ICCF 17, I spoke about the electrolysis system. We're not going to talk about that here. That's a high pressure, 1000 psi, 120 to 150 degrees C electrolysis of nickel, normal water, light water, and they're able to control their pulses. This one actually has 2 different pulses, one going between the cathode and anode, and one going axially along the cathode. And excess power depends on pulse repetition rate, pulse amplitude, pulse width, and all the parameters that you would control if you're an electrical engineer, and that's what's consistent with the controlled electron capture hypothesis. They're able to see 25 to 100% excess, and they're able to turn it on and off by changing the pulse parameters. This is the newest of their cores. They call them cores. That's their reactive zone inside the reactor. This one is actually built on a cartridge heater, and they coat that with copper, and then they coat that with a ceramic, most of the time alumina, and then they coat that with nickel. And the whole tube, the core is about 18 inches long. It's coated for about 16 of those inches. The heater, unfortunately, has a thermocouple inside it, and that only fills about 6 inches of the middle. And the important part of that is that when you put pulses through the nickel, it heats up the whole core, but the temperature that you measure in the middle is not all the power that you put in. Some of that is lost. In fact, about half of it is lost. And that's just one example. Sometimes they put palladium with palladium alloys underneath the nickel. Sometimes they put other metals on that system. Okay, yes, this is an idea of what their pulse looks like. It doesn't look anywhere near that symmetrical. The pulse width is in the hundreds of nanoseconds, and the separation time could be 10 microseconds. So it's probably less than 1% duty cycle. And we control the voltage, control the repetition rate, and things like that. And by being able to control all of that, we can have constant pulse power. So the amount of power going into the nickel is held constant. As you come down to the bottom side, is where we measure the power going into the pulse. So it has a high-speed oscilloscope taking about 1 million data points across that one pulse train. And that measures the voltage at one end of the core and measures the voltage at the other end of the core. And then you see that termination resistor labeled Z-term is their current shunt. And by measuring the voltage across that current shunt, you can get the current. The bottom right graph gives you an idea of what you're measuring. That's the rise time of the two voltages. And so they just align the two voltages as well as possible, ignoring any potential phase lag, simply because there is actually a transmission time across the length of the core, which is on the same order of magnitude as the rise time. And so by simply assuming that there's no phase lag, they're actually making a conservative estimate of the power. They're overestimating the power. And then up in the top right, there we go, up in the top right, that is the subtraction of the two voltages down here. That is the current, or the voltage across the current shunt converted to current, and that's the product of those two. And you can either do an SWR calculation or simply integrate under the curve to get the power actually entering the core. This is just their HMI, the computer interface. The only point I want to make here is there's about 43 different parameters collected by this system, and gives you a good idea of what's happening in real time. And okay, this is the apparatus itself. Call it isoparabolic. Some people call it isoparabolic. I did a literature survey the other day to look that up, and almost all the people who call these things isoparabolic are in the cold fusion or Leonard field. Most of the university people call it isoparabol, but either way, I'll refer to it as IPB. And so here's that core down the middle. The heater's in the center, just covering a small portion. There's a large copper block here, which still doesn't cover all of the core. And then an alumina or ceramic insulation, and then an aluminum shell on the outside, water flowing between that aluminum shell and the acrylic shell. There's one temperature sensor embedded down in the heater. There's another temperature sensor embedded in the copper block. That's the inner temperature sensor of a typical isoparabolic calorimeter. There are two temperature sensors embedded in the aluminum shell. That's held at constant temperature by the flowing water, and that's the outer temperature of the isoparabolic calculation. And then the pulses are introduced here. So they run it either in helium, hydrogen, or D2. I keep saying they. I just got one of these last Tuesday, and I haven't had a chance to play with it and kick the tires. So all the data I'm going to be talking about was actually run up in the Brillo and Berkeley lab. They hold the core from 200 to 600. The outer block temperature is held constant. The pulse power is held constant, and the actual pulse power is measured directly. And the big difference here, this is not run like most of the isoparabolic calorimeters you have, where you keep the constant power. In this one, we use power compensation, so we keep all of the temperatures essentially constant and measure how much power is necessary to do that. And the difference of that power with and without a pulse gives you an idea how much power is coming out of the core. This is the protocol. Vary the temperature. We use a DC power across the core to calibrate how much power is going into the core and how much is actually being imparted into the central heater. Remember, the power compensation is by this heater, which is only in the center of the core. core, so it doesn't see all the power that's being imparted to the full length of the core. So we have to calculate what that percentage is. So we do that, and then we repeat it. Hydrogen, there's my 5-minute point. And measure and record the 43 parameters. You can see all the heater powers, pulse powers, temperatures, flow rates, pressures. And they measure hydrogen and oxygen outside just for safety. The temperatures are important. We found it's extremely temperature dependent. And like I said, different width pulses. How they keep the power constant with different width pulses is they keep the voltage constant, so the voltage amplitude is constant, but they keep changing the repetition rate. So as you increase the pulse width, you decrease the repetition rate. And so the power to the heater is the only thing that's changing. I'm not going to go through this, but this is where I talked about calibrating that with a DC. You simply do a linear plot, and you can figure out what that percentage is. B actually tends to be very small, and M tends to be in the 50% range. So then you put in your heater before, heater without the pulse, heater with the pulse, either with DC or the pulse. That's this delta Q heater. Delta Q out is this calculation of M times the pulse power right here, and you add B back to the heater, delta Q here, and you divide by the pulse, and that's the COP calculation. This is what some of the results look like. Constant 600 degrees. There's no pulse here, no pulse out here. You can see the pulse power coming in, the pulse width, 300, 150, 100 nanoseconds. And you see the heater power is pretty much constant. Did we go too far? Okay, that's actually, yes. All right, and this is what it looks like at 300 C, and what you can see, it's quite different. Unfortunately, this does not pass the, you can see it from across the room test, so we actually have to do the calculations to find out if there is any power in there. And those are shown here, again, without getting into it. There's the heater power difference with and without pulse. There's the power measured by the scope. There's the power measured by the scope multiplied by the correction parameter, and you can, these are at different temperatures, 150 to 400. You can see at 150 and 400, it's near 1. In the middle, it's a little higher at 300, which is what we've been finding. On the next slide is a summary of some of the better results. And again, I point out here at 600, it's near no excess power. And at 300 and 250, you see numbers between 25 and 40%. And they have seen numbers much higher than that. And okay, so this is a quick summary in future work. Stimulated by electric pulses, hydrogen and helium at 200 to 600, do the exact same procedure. The helium, they just don't see the difference in temperature. We don't compare hydrogen to helium. It's just there to show that the system is very stable when you put in pulses, and it's irregardless of temperature. Power compensation mode, which I described, 100 experiments in 8 different nickel-coated cores, and numbers up to 2.0. We're still optimizing the metallurgy and hoping to use other metals and alloys, and better calorimetry by making the heater the full length. And hopefully we can pick up 100% so we can get rid of that correction factor, which always upsets people. But these calculations are nowhere near as complicated as some of the isoparabolic calorimeters that Martin used to describe in the early days. And this is actually just part of the Berlin group up in their office, their labs behind that door. where they have those high-pressure reactors. I want a special thanks to Mike. He and I and these guys spent a lot of time designing this new calorimeter. Thanks to a bunch of the other guys from Brilloin who helped with the data analysis and calorimetry. Acknowledge Brilloin Energy for funding this work, and thank you for your attention.
Thank you very much. Do you have any comments, questions?